Looking at day 2 of section 11.1, which deals with parametric functions. Hey, we're going to focus on the arc length today. And first, let's just define how to capture or how to calculate the arc length of a parameterized curve. So we have a curve and we want to calculate the length along it. So what we're going to do is kind of use the distance formula, change of x squared plus change of y squared, and think of it as being little segments added together, just like we did when we were on normal arc length of rectangular curves. So it's going to be just a slight bit different. You can see the formula here. And you can see the distance formula, and here's change of x squared, here's change of y squared. And then we'll integrate, notice the parameter now, t, from a certain t to a certain t, becomes our bounds on the integral. And then it's with respect to dt. If you wanted to work on this formula from before that we knew, here's the formula for arc length under rectangular. It's 1 plus dy dx quantity squared dx, square rooted. It can transfer over. Let's just update what dy dx is calculated at in the parametric equation side of things. So now we've got to have dy dt over dx dt quantity squared. And then this is the one that's a little bit tricky thinking of. If I took dy dt squared and multiply by the reciprocal of this, flip it over, that would be equivalent. And let's say I wanted to factor that out. Yeah, let's just say that. Let's just say, hey, I think I should factor out dt dx quantity squared. Well, then I have to adjust this 1, right? Because this would distribute to each of those. But notice how we're going to put in dx dt, just the reciprocal of dt dx. And when I do distribute through, what happens here? It becomes 1. So I had to kind of be creative here to make that 1 happen. And then if I multiply by here, well, now I'm back to this scenario, which we know is equivalent to dy dx, really. Okay, we've got that settled. Now let's say, oh, I can take the square root when things are multiplied and I got something squared. So if I do that, that's going to simplify by moving out to a dt dx. And underneath, I'm going to be sitting with dx dt squared, dy dt quantity squared. But I've got dt dx, dx cancels with dx, and voila, we have been able to transform from the rectangular arc length formula to the parametric equation arc length formula. Okay? It's kind of nice to see proofs once in a while, especially when you're starting to move into upper level math. All right, so let's just do a problem. Here's an asteroid. It's a particular type of mathematical curve. It has 4 cusps. They're also called superellipses. If you can imagine this circle moving around and tracing out, this particular is going to trace out, whoops, let's make that hit. As the circle's rotating within the circle, think spirograph. You've seen this happen if you've played with spirograph. We would get this hypocycloid formed. And so there's the 4 sides of it. Our t is running between 0 and 2 pi. So that's going to trace out all 4 sides. Now, from 0, when t is between 0, that's where the point would start. And if I just went up to pi over 2, it would finish there, right? I would get the xy coordinate when t is pi over 2. So I could really look at just that first section and multiply by 4, because all the others are going to have the same arc length as that first quadrant has. So I think I'm going to use that idea of multiplying by 4 and just integrate between 0 and pi over 2. Okay, so we have our two functions defined as cosine cubed and sine cubed. Find the arc length of the asteroid. Find the derivatives. Well, yeah, we're going to need derivatives because if I'm coming into the arc length formula, we know what that looks like. Let's see. dx dt would be equal to 3 cosine squared t chain rule times negative sine of t, and dy dt is going to be equal to, let's work with the outer function, we got some chain rule, 3 sine squared t times the cosine of t. So we know our dy dt and our dx dt. Then when I come to my arc length formula, what is arc length? See if you can recall it without looking. That long proof we just talked about. We are going to integrate from 0 to pi over 2, and we'll multiply by 4. And I need the square root of dx dt, quantity squared, plus dy dt, quantity squared. No problem, we did that calculation. So 0 to pi over 2, square root, dx dt. So we're going to have to square this stuff. That'll produce a 9 cosine to the 4th t sine squared t, added with dy dt. So now we're going to square this one. A little bigger square root, just extend it. 9 sine to the 4th t cosine squared t with respect to t, so dt. Oh, that looks like fun. Now, if you had a calculator, which you might actually have, you could just toss it in the calculator and get your answer. This one we actually can do by hand, believe it or not. We just have to do a little simplifying. And I think you see that they have the 9 in common. So let's factor that forward. They also have cosine squared in common, right? I could pull that. So let's write down the cosine squared t. And what other thing is still in common? A sine squared t, because I have sine to the 4th out of the other one. So I could pull a sine squared t out of that. And that will be multiplied then by, okay, the 9 got pulled out front. I took a cosine squared, so I'm going to be left with a cosine squared. And here the 9 was pulled out, but I didn't grab all the sine squareds, or sine to the 4th. I took a sine squared, so I'm going to be left with a sine squared dt. Ooh, key point, this was a plus sign in between. Let's throw that in a different color. Plus sign sitting between there. That was key because what is cosine squared plus sine squared? Oh, yeah, it simplifies to 1, doesn't it? And this 9, why not move it out front as a 3? So now I've got 4 times 3 out front, square root cosine squared t sine squared t. Ooh, that will simplify because it is connected with multiplication. All right, so now we're at 12 integral of 0 to pi over 2, and square root each of these, and we're talking, I'm going to rearrange this for a moment, sine t, cosine t, dt. How do I integrate that? And good question, huh? No, it's easy to integrate that because let u equal sine. You also could let u equal cosine, but it'll be a little cleaner if we do sine because I won't have a negative. The derivative of sine is cosine without a negative. So there we go. So this actually turns into the integral of a u du, doesn't it? All right, that's easy to integrate. That gives me a u squared, or a sine squared t evaluated from 0 to pi over 2. I didn't want to go back to u's, you guys. I just am going to stick with t's, and I don't have to update the bounds and all that fun stuff when you're integrating and doing u sub and stay in u's. All right, we should be able to do this math. This doesn't look too hard to us. We will start at the top, right, fundamental theorem, and we'll have the sine of pi over 2, calculate that, and then square that answer, minus the sine of 0, square that, and that'll be our answer. So I get 12. Sine of pi over 2 is 1, and I did something. I know I did something. I forgot a 2 there, didn't I? I upped the power. This would have been a u squared over 2. There's my 2. So let's bring the 2 out here. See if you can get your notes caught up on that, guys. Sorry about that. So I have 1 minus 0, sine of 0, 0. And we get 12 divided by 2 is 6. Has a arc length of the asteroid of 6. Not too bad. This isn't really that hard. Formula driven, right? The next one, calculate the perimeter of the ellipse generated by the parametric equations x of t equals 3 cosine t and y of t equals 2 sine t. And in order to find this ellipse, in order to integrate it, I would need to find the limits of integration. So if this, maybe just a little check out, if I have t at 0, where does this begin? My x value, my y value. If I put in 0 to cosine, I'm going to get out 3. If I put in 0 to the y value, I'm going to get 0. And then if I do pi over 2, let's just check that out. Pi over 2, I would have the x value being 0, the y value being pi over 2, 2. And then you could check, if I do pi, I have a feeling it's going to be negative 3, 0. And if I do 3 pi over 2, I have a feeling it's going to be 0, negative 2. And if I bring it back home at 2 pi, I'm back at 3, 0, where I began. So this thing will map out as a 3, 0, a 0, 2, a negative 3, 0, and a negative 2, 0. And our ellipse should be wider than it is tall. That makes sense. How long did it take to trace that out? From 0 to 2 pi, all these points would map out, right, to complete the cycle. So you're seeing the start up here, 0 to 2 pi, and that's how they got that. And then we know that it's the dx over dt squared plus the dy over dt squared. So you've kind of got it somewhat set up. Now, I think I would do this by hand rather than asking my calculator to do that, because this is pretty simple. It is a 2 times the 3, so we're talking 6 cosine t. Derivative cosine will be negative sine t, so I threw my negative out front, plus sine, or chain rule again, 2 times 2 is 4. For sine t, derivative of sine t is cosine t dt. And I don't see any real sweet tricks to do on this one. So I think what I would choose is to use my calculator. So for many arc length problems, you're going to have access to the calculator, and this would turn out to be 15.865 for our answer. So you'd be able to pop that in, get your answer. Example number 3, a particle travels along the path. Describe parametrically x of t equals 2t and y of t equals 1 plus t to the 3 halves. Find the following. First off, they want the distance traveled. Distance traveled along that parametric curve is synonymous with arc length. not sure if I mentioned that when they said perimeter. I guess I automatically interpreted that as arc length as well, right? So the distance around, that'll be an arc length in parametric terms. So this is really asking for the arc length during the interval 0 to 4. And for this, we will use, I guess, here we go, the arc length formula. So now I just need to have that memorized. Length equals 0 to 4 because they told me about that. And I want the square root of the derivative of x squared, so it's going to be 2 squared, plus the derivative of y squared. And what is that derivative? 3/2 t raised to the 1/2 squared dt. And maybe just simplify before I use my calculator. 0 to 4, square root 4 plus square the half, that's going to make it a 1. So a 3/2t dt. Maybe for ease of putting it in the calculator, I might even call it a 1.5t. I don't have to worry about fractions. That, if you use your calculator, will give you an 11.52. Displacement. Oh, we've heard displacement before when we've worked with particle motion. Displacement says, where did you start? Where did you finish? Doesn't matter how you travel to get there. Displacement just cares about starting to ending. So this would be displacement, wouldn't it? Which means, how did I get from point A to the finishing point B? In order to do that, in arc length, we are going to use the distance formula. So, I guess that was an okay picture too. Maybe if I had a simple curve like this, arc length would have been all along there. Distance would be this. And I'm mixing my words. I'm so sorry. I should say displacement. To imply beginning point A to ending point B. The other thing along here would be known as arc length or distance traveled, which is a different answer than using the distance formula. That's what gets a little confusing, doesn't it? All right, in order to use distance formula, what the heck is the distance formula, you ask? Well, displacement will equal the square root of the difference of the x's. How'd you usually write that? x2 minus x1 quantity squared plus y2 minus y1 quantity squared. Good old middle school stuff. In order to do that, I need ordered pairs. In order to get ordered pairs, I've got to attack it from my beginning point and finish at my ending point. I need the ordered pairs of that. All right, so when t is 0, I have x of 0 turns into, where's our formula? Up there, 2 times 0, that gives me 0. Y of 0, I put in 1 plus 0 to the 3/2. Well, that sounds like it's a 1. We got an ordered pair of 1, 0. Holy cow, a 0, 1. It's only like, 6 o'clock right now, guys, and I've been here at school since like 6:30 this morning. Now, t equals 4, and into the x equation, x of 4, dang it, I lost, well, that's because it rolled off the screen. We want to put it into 2t, so x of 4, 2 times 4 makes 8. Y of 4 is a 1 plus 4 raised to the 3/2. You know what that means. You got to be able to interpret a rational exponent, square root, quantity cubed. That is a 1 plus 2 cubed. That is a 9. Okay, that's an ordered pair that gives us 8, 9. Now for the magic. Displacement. Equals the square root. X. Why did I point to Y? Okay, retry. X minus X. Quantity squared. Y minus Y. Quantity squared. Can you do the math? 64 plus 64 and 64 and 64 makes square root 128 as a decimal 11.314. If you wanted to simplify your radical, this would have been 64 times 2. That's an 8 root 2. All right. That is the rest. That finishes section 11.1. Your assignment is to complete that stuff, which we kind of had assigned up to that point yesterday. So really it is completing the arc length questions and a couple of the multiple choice questions there in short answer. All right, now the other thing I'd like you to work on or complete, let's not just say work on because I know what that'll look like. Let's do the worksheet that follows in your book, you guys. I believe there are 11 questions to this. Oh, yeah, I've got them spread out. 6. Oh, heavens, we want to get off that page. I'll pause here so I can look, see what that assignment's going to be. Okay, so the worksheet that I was showing is different in your notes because I've revised it. So I would like you to do 1 through 11, which is all the multiple choice. So this is an AP worksheet, and it's those multiple choice. Do all the multiple choice on that. And then I think when we come back Monday, we will probably finish those free response ones. Maybe that's what we'll do in class on Monday. I'm looking for a quiz that covers 1.4 and this 11.1 probably on Tuesday. So quiz coming up on Tuesday. Keep that in mind. Hey, have a good weekend, guys. See ya on Monday.